Everyone, this is the problem that we are skipping from the 2013 E&M exam. It's a great question. I love it. And I think it's one that I want to take off the eligible list of problems for this particular test, just because the physics is straightforward and the algebraic rearrangement is a little bit more trouble than it's worth at this point in the semester. But we will revisit it later. So just to be clear, this problem, we will just make a note that we are not going to worry about it. So not on the test. So continuing on, we will take a look, and we'll get rid of this too. Whoops. Well, what's going on? There we go. All right. Continuing, the 2014 problem, we have a DC power supply and an ammeter. This little A is a device that measures current and offers no resistance in the circuit. And what it's telling us is that we have this variable voltage and we have various currents coming out of this DC power supply. So what we're doing is we're going to plot the data points for the current as a function of potential difference. And I'm just kind of curious what we're looking for here. Okay, I guess we're getting the total resistance, so that's cute. So with that in mind, it says we are plotting current as a function of potential difference. So that means the potential difference will be here, and the current in milliamps will be down here. So let's be clear that this is times 10 to the negative 3. In other words, we'll need to take a number from this bottom part and times it by 10 to the negative 3 if we want to convert it into a current that we can use in a calculation. So I is going to be in milliamps. And it seems that we're going from 0 to 155. So let's just see. Let's see, 50, 100, 150, 200. I'm going to make my life easy. Well, I suppose I could go 1, 2, 3, 40, 80, 120, 160, and 200. And then I'm counting up by 8 on these here. And then for my potential difference, I'm going all the way up to 10 volts. So I suppose I could make this 5 volts and I could make this 10 volts. That means that each of these squares is actually half a volt. Okay, so with that in mind, let's go ahead and just label things. So we have 2 volts when we are at 40. So we have that mark right there. And we'll include 0, 0 just to be safe. And then when we are at 55 milliamps, we're at a voltage of 4. So this is 48, 56, because we're counting by 8. So again, 1, 2, 3, 4, 5 8s are 40. So 48, 56, so about 55 right there. And according to this thing, we are at, how many volts was it? 4 volts. So 5. So right there is where we'd be for our next one. Then at a current of 97, we'll be at a voltage of 6. So 88, 96, 97's a little bit right there. And we'll be at a voltage of 6. So that works. And then at 138 to 128, 136, that'd be 140. So about right there. Will be at a voltage of 8 volts. 7.58 right there. And lastly, we're at, 128, 136, 144, 150. So about 155 right there, we're at a voltage of about 10 volts. So this isn't necessarily the best set of data. But it does get the job done. Now, I'm going to try to do this using this program. I'm going to draw a line just connecting the beginning and end point, or at least trying to do sort of a best fit line like this. All right, this is close enough, is what we're going to call that. Maybe I'll just, there we go. Close enough. Now let's pick 2 points on this line and get the slope. So the slope here, these 2 points, so this is 80 milliamps and 5 volts, and 40 milliamps and 2.5. So let's make sure I have that right. Yes, I had that right. All right. So with that in mind, I'm going to go ahead and actually calculate then with these 2 points in the next page. I'm going to use the slope to get the total resistance of the 3 resistor combination. So I'm actually going to do part, let me make sure I have the part right. Yes, that'll be part B right here. So I can say 5 minus 2.5 divided by 80 minus 40, but be careful, this is milliamps, so I need to times it by 10 to the negative 3. So being very careful here, this is going to be 2.5 divided by 0.04 when I take 40 and times it by 10 to the negative 3. So I'm getting a total resistance of 62.5 ohms. All right. So that is what I get for the resistance. Now let's get the value of just R1. So we know the total resistance is 62.5. So what we can say is the following for part C. We can say that R23, they are in series. Again, I don't know what's going on, but people are under the impression that these 50 and 50 are in parallel. They're not in parallel. There's no way to branch out. They have a parallel line, but parallel lines have nothing to do with parallel resistors. They're in series because the current is forced to go. The same current that starts here absolutely has to go through R3. That's why they're in series. So to combine these, what we're going to say is R23 is 100. R123 is going to be 1 over R1 plus 1 over 100 to the negative 1. Keeping that in mind, we know that R123 is 62.5, which we got from that slope calculation. So what we can say using this math is 1 over, and I'm going to actually continue this right here for part C. I'm going to say 1 over 62.5 minus 1 over 100 equals 1 over R1. So we'll do that math. And then that's 1 over 0.006. And when we actually take that, we're getting that R1 is going to be 167 ohms. Okay. Now, the power supply is fixed at 12 volts. We're going to calculate the current through R2. So let's do part D in a different color. And we'll go back to this first page here. So if we have 12 volts in part D, and we know that this is 167 ohms from part C, we can do a little bit of combination. We want the current through R2. So let's go ahead. We know that here we can combine the resistor We know the combined resistance is 62.5. We calculated that in a previous part. So I total is going to be 12 over 62.5. So 12 divided by 62.5 gets me 0.192 amps. Now I've calculated that. I'm not clear on how that's useful yet. I just wanted to go ahead and calculate it. So let's look at some other things. Okay, I have a 12-volt battery here. I also know that R23 as a combination is 100 ohms. So where does that lead us? Let's see. We want to know the current through R2. We know R23 is 100. Here's what else we can say. The 12 volts is in parallel with R1, and it's in parallel with R23. So R1 has 12 volts on it, and R23 has 12 volts on it. So I can get I23 as 12 over 100, and so that's going to give me 0.12 amps as my answer to part D, because that's I23, which is the I through 2 and the I through 3, since they are in series. All right, now we're going to replace this resistor 3 with a capacitor. We want the current at R2 after the switch is closed. So immediately after it's closed, we've got 12 volts here. And again, we have that R1 is 167 ohms. So we have 50 in parallel with 167. So we can actually just take this as the loop. And you know what? Let me actually just switch colors again to be clear on what we're working with. Sorry to anybody who struggles with colors. I'm trying to pick better colors. These may not be the best ones. So here we will pick, this is 12 volts. This is 167 ohms, and we have 50 here. Now, since 50 and 167 are in parallel, when we close the switch, this acts as a wire. So I can do a loop like this and just say 12 volts minus the current through R1 equals 0. And so I can say 12 volts minus I times 167 equals 0. So the current through R1 is 12 divided by 167, which is 0.071 amps. They didn't ask for that, did they? I did the wrong part. They asked us for the current through R2. So I through 2 similarly is going to be 12 over 50. And that's going to give us 0.24 amps. Moving on. After a long time the switch is closed, what's going to happen to the current in R2? After the switch is closed, this capacitor is going to charge up. So we're going to have less current because the capacitor charges up. Lastly, if we replace the capacitor, R2 doesn't change because both act like a wire at t equals 0. Both act, oh my gosh, that's terrible writing. They both act like wires at t equals 0, so their capacitance doesn't matter. So that is the answer to the 2014 practice problem.